So if you're sitting in the back, you might want to think about that because our screens are pretty small. I'm not sure how legible things are going to be from the back of the room. So if you see an open seat in the first couple of rows, you might want to think about moving up, especially once we see how things look once we get going. So if you followed this link, you will have ended up at our Etherpad. This is a kind of like a collaborative document. So we can all type in here. There's a little chat over here where I can say morning. And then everybody can type over here in the main area to kind of make this collaborative document. Make sure you set your name over here by going up to the top and clicking here and set your name. Those of us helping will be watching this. You can ask questions here in the chat. We'll do things like paste commands you need to type or links you need to follow into the document here. So just have this open because it comes in handy. Please make use of it because we'll try to keep an eye on it.
And we'll save it at the end so that it will continue to live on and you will always have access to it.
Okay, so a couple of introductions. Yes.
Can you paste the Mozilla link in that Etherpad too? Or the Etherpad link at the top of the Etherpad?
Oh, this is small.
Yeah.
Because it's in the back. Oh, okay. So you can follow this longer link here to get to this, since my other window is in the background. Okay, so introductions. Hi, I'm Matt Davis. I'm in charge of this thing, but I'm actually going to be at the front of the room, not a whole lot, or not any more than any of the other awesome people we have here. So can I get all of our other instructors and helpers to stand up / raise their hands and make themselves visible and well known? So we've got Jens, Azalee, Jess, Thomas, what do you go by Ted?
Yeah.
Ted, April, Katie, and I think we've got one more. So all of these people are, whichever of us is not at the front of the room at any given time is ready and willing to come jump to your aid if you get into trouble. Use the Etherpad or raise your hand, or we have these sticky notes. We passed out all of these sticky notes to you. When you need help, the little pink sticky note is the I need help flag. And so if you can put that up on your the back of your laptop, one of us will look for it and come help you. And I think our last helper, Elizabeth, just came in. Thank you for coming, Elizabeth, all the way here.
Nice subtle entry here.
So we've got the Etherpad, we've covered the sticky notes. The green sticky notes you'll use, we'll do exercises. When you've completed the exercise, put up your green sticky note on the back of your laptop so we can tell how far along people are, like when you're done. So that's what the sticky notes are for. This is our main website, which has a lot of links to things. But like I said, we'll put most of those here in the Etherpad. Question?
Yeah, but I don't know what we're talking about as far as sticky notes.
You didn't get sticky notes right there. Okay. We'll take care of that, thanks. If you don't have sticky notes yet, signal Jens as he comes around. Okay, so let me introduce Software Carpentry, which you have all signed up for. Hopefully, everyone's here for Software Carpentry, right? Okay, good. Okay, so as you all have done your research or done your work, whatever it is you do, you have probably figured out that programming is a pretty big part of your life or is becoming a pretty big part of your life. And that may be going along with varying degrees of success. It was certainly a pretty bumpy road for me the first couple of years. I was doing a lot of programming. And what they don't tell you in school a lot of the times is that programming is a full-time job for a lot of people, right? Obviously. I'm one of those people nowadays. But those people, software engineers and professional programmers who have been doing this, who have been coding for a long time, have gotten frustrated with all of the same things that you get frustrated with as a programmer, and have invented different tools and different techniques and best practices for dealing with those frustrations. But a lot of the times, researchers don't get exposed to those things. And that's what software carpentry wants to do. Software carpentry wants to help you learn a lot of the tools and techniques that professional software programmers use to keep themselves sane, writing code all the time. As someone who writes code pretty much all day, every day, I can tell you that everything we are going to teach you about is the only thing that has kept me out of the insane asylum. Like, it's absolutely critical once you get more than like waist deep into code. So this morning, we are going to talk about the shell, or a terminal, which is a way of giving your computer commands by typing. And that might seem a little slow and burdensome at first, but you're going to see actually how powerful it can be. Way back in the day, when computers filled up rooms, typing was the only option you had for talking to your computer. But people still needed to do all of the things you do today with your mouse and the fancy windows and everything. And so they invented a lot of really powerful shortcuts for getting all of that stuff done. Not shortcuts, but short commands and clever ways of doing things to get all of that stuff done very quickly just by typing. So I think probably all of us as instructors spend all our time in the terminal and not a lot of time looking at windows. And then this afternoon, we'll start covering Python, which is what you're all here for, obviously, at SciPy. But we'll just introduce Python and get you used to the Python syntax and doing basic things in Python. Tomorrow morning, we'll talk about Git, which is a version control system, which is a way of tracking changes to your code so that as you're working, you can always say, you can make little check-ins of your code, little snapshots, and always be able to return to them. So even if you have really wild ideas about crazy things you want to try, that end up changing half of your code, and then it doesn't work out and you have to go back, you didn't have to make any copies, you didn't have to do anything fancy. You can use Git to go right back to where you were, no harm done. And then tomorrow afternoon, we'll introduce some of the scientific Python libraries that you're going to hear about for the rest of the conference. And kind of get you started on that. So 2 days is a very quick introduction to everything we're going to cover. So it's going to go fast, and we're going to give you a lot of information. So make sure that you've got your coffee or whatever it is that keeps you awake, and that you eat your snacks and stay on top of things. We want everybody alert and happy. Are there any questions?
I would also say when we give you a break, like, stop looking at your screen, stand up, go outside, meet your neighbor. It will keep you awake and much more alert.
On the topic of meeting your neighbor, it's a good idea to be sitting next to somebody besides one of us, sitting next to a fellow student so that you can work together. When we're doing exercises and having downtime, we love to hear lots of chatter. We want you all talking to each other, getting to know your neighbor, and collaborating. When we do exercises, they're not quizzes, they're not tests. It's absolutely the best if you actually talk to each other and work through the things together. You will learn better that way. So please do that. Okay, any more questions before I hand things over to Jens for the shell? All right, let's give it to Jens. Everybody's in the Etherpad?
Do you want everyone to just type a hi message, because I'm seeing only.
We've got everybody here, but they're being quiet. You have a question?
Yeah, I'm not sure how to get on this message, and I got it open, I see everyone else on
Okay, that's all you have to do. To actually say hi, you can go down to the lower right-hand corner where it says chat and type something. So if you have questions, put them there into the chat. And then we'll be kind of taking notes and putting in links and stuff over here on the left. And Jess, has this guy taken care of? All right, I'm going to unplug and let Jens get set up.
Does this look readable from the back? Don't hear anyone complaining, so I'll assume that this is workable. Yeah, so we are going to start off with the shell session today, and this is the example of the shell running on my computer. So how many of you have any experience in using any kind of shell before? So about half have some kind of experience, and I assume the rest doesn't. So we'll take this. We'll start with pretty basic stuff to get this working. So it would be good, as Matt said, then there's a link to the software carpentry materials on the shell, and we'll be following those pretty much all the time. It would be good if you could start by creating a directory somewhere on your computer and calling it something with shell, software carpentry shell, and then we'll work from that directory and put all our files in there that we will manipulate with. If you go to the Etherpad and follow this link to the materials on the software carpentry, then you can see here it says download, and there's a file you're asked to download. So please go ahead and do that, download that file.
Your green sticking out when you successfully downloaded that file. When you're red, sticking out.
Yeah. And once you've downloaded it, then unzip it and move the data folder into the directory that you just created. And then put up a green sticky note once that's working. You should just use your regular Finder, Windows Explorer, or Linux thing to move the files around for now, and then we'll show how to do it with the terminal later on. So let me just do the same thing.
So some of you may have done this already, because it was part of the set of instructions. Does everybody know how to open a terminal? If you're on Windows, you're going to be opening Git Bash. If you're on a Mac, the normal, or on Linux, whatever normal terminal you use.
Yeah, so on the Mac, I'm using one called iTerm, but it really doesn't matter. Normally, you can use your Spotlight search and type terminal, and then you'll get this window, which are, for all practical purposes, exactly the same thing. No, it's not crucial exactly where you've got that folder. We just want you to have the folder data somewhere in your home directory so we can work with stuff in it.
Yes, I will also say, ask for help sooner rather than later.
Yeah.
Because everything we're doing builds, and we have so many people here to help that we would rather get to you at the very beginning before you've missed half the lesson.
Yeah, and please, raise your put up the sticky note or write in the Etherpad to do something, because obviously we're all here to help. And also if you've got if you manage to open a terminal window that looks something like this.
But it may be the wrong data that I have.
We'll see about that. The data directory.
There's something else.
So the data directory should contain 4 folders called bin, data, temp, and users. We will. So once you've opened the terminal, then you can use ls to see what's in your folder, but we'll show that later. Is the last line readable, or should we move the display up and only use the upper half? Like that? Right, so once you've downloaded the file, the folder, and placed it somewhere, we should be able to navigate into that directory. In my case, I left the data inside the directory called SciPy 2015, so I'll do cd SciPy 2015, press enter, then I've navigated to that directory, and then I'll do cd data and navigate into that directory. Then I can use the command ls to see what's actually inside the directory. And in this case, there are 4 folders called bin, data, temp, and users. Please take down your green sticky note and put it up if you can get to as far as here. If not, then okay, I think. Anyone still having issues that, are you all right? It's working, great. Well, let's carry on. We've seen just a little bit of how we can navigate, and we navigated in. You should always all be in the position of having used cd, which is short for change directory, to navigate into the folder that we downloaded, and ls to list the contents of the folder. And we see that this contains 4 different directories. Now, Matt already gave sort of a brief introduction to what the shell is about, so I'll go right into actually starting to use it. So in this case, this data folder that we downloaded represents the contents of someone's computer. So we can use the command pvd for print work directory to see where we are. So in this case, it tells us that we're inside the users JHN, which is my username, SciPy 2015 data directory. And that directory contains these 4 folders. On Linux machines, then it will store stuff under home rather than users, but the principle is the same. On the Windows machines, git bash represents this a bit differently, and it starts with a /c for your C drive. But the principle remains the same. That this slash at the beginning represents the root of your machine, so the very top level directory. So if I do cd /, then I'll be put at the very top of my machine, and I do ls, then I can see the contents of that thing. If you do ls.f with a large F, then it will give you some help. So we'll put a / at the end of some of the folders that shows that these are actually folders, where stuff that doesn't contain a / is a file. in my case, I've set something up that colors them so to represent the same data, but you can use /f to show that. So I'm going to navigate back home to my home directory, which was /users jhn, and then we're navigating into the SciPy directory and the data directory. Now, this data directory contains the home folder of another person's computer. So we're imagining that we're going through some data analysis that Nell wished to perform on data that she's collected in a scientific expedition to the plastic isles out in the North Atlantic. And she's collected a whole bunch of data that she needs to run the same script on over and over again. But she's collected several hundred files. Each of them takes a few minutes to process, meaning that if she had to process all this data manually, she would have to be every second minute typing in a new file name, pressing OK, doing the analysis, and then moving on to the next file, which will be tedious and obviously not a good way to spend her scientific research time. So what we're going to focus on is to show how we can use the shell to automatize these kind of tasks so that you just have to start it once, and then it goes through the analysis of all the data files. Yeah, so a few other basic things that we can show. We've shown ls to see all the directories in there, ls/f to show that they are what's directories and what's files. We've shown that we can use pwd to tell us where we are. That can be very important because obviously we could have several directories inside each other. They could even have the same name. So if you don't remember where you are, then you can easily get lost. So then pwd comes in handy as a way of telling you where you are. Another command that you can use is whoami, which will tell you which user you're logged into on your machine. In most of the cases here, you will be running at your laptop, so you will probably be the only user of that machine. But for some of you, you might want to use this to do data analysis on a supercomputer or department cluster or something like that, where several hundred different users can exist, so you can confirm that you're actually logged in as the user you expect to be. So what actually happens in the background here is that when I type in this, then the shell goes ahead and interprets that I want to run a program that's called whoami. And actually I can use the command which to tell me which version of where this program is that I'm going to run. So in the folder user/bin, there's a program called whoami, which is the one I execute when I type whoami. So what happens when I do this and press enter is exactly the same thing that would happen if you had a program on your desktop which was an executable and you double-clicked on it to run it. The program runs and then it prints out some output and so forth. That's the concept. Yeah, we've already talked about home directories. We can explore a little bit more of what's inside this data directory. So we can see that this contains a users folder. Imagine that this was the directory data here is the root of Nell's computer. Then we can see that in the same way as I've got my users JHN, then this one's got users. Then there's Nell's home directory, Larry's home directory, and Imhotep's home directory in here. Any questions? Was that a general question?
Just me.
Yeah. ls has several other options that we can show. So we can see what's inside nil's directory by doing ls nil without actually going in there. And so on. Another thing which we should show, so we've seen how we can navigate forward by doing cd, so we can do cd nil. If we actually want to go back to the directory where we just came from, then we use the shortcut cd double dot. So double dot is a shortcut for the directory just above the one that I'm in. So we do pwd and we do cd dot dot. Then we can see that we've moved up one directory. The other way of navigating is, of course, that we've shown that we can do it via an absolute path. So if we start with a slash, then we signal that this is an absolute path that begins at the very root of our machine, and then we could type in all of it. But obviously, doing that every time you want to move somewhere gets tiresome and cumbersome. Any questions about these basic navigation around folders? Should probably spend a few minutes experimenting, going back and forth into various of Nell's folders and making sure that you're comfortable with going in there and going out again and exploring what's in these folders inside data. Once you're happy with that, then put up a green node.
You want to mention tab completing?
Yeah, so that's probably the thing that I've been doing unconsciously. So on most machines, you can actually tab complete. So when I do cd, I type the first letter and then press tab. Then it will automatically look which things can you cd into that starts with a U. In this case, the only possibility is users. So that comes in handy. If I press tab again, then if I keep pressing tab, it will eventually show me the possible things that I can complete it to, and so on. Which can save you a lot of time because you don't have to cd, do ls, cd, do ls, but you can actually just type tab. Yeah, so play around with this and put up a green sticky note when you are happy. And a red sticky note, of course, if there are any issues. All right. So we talked about that this is going to be we are going to use this example of Nell's research data from the North Pacific Gyre of some samples that she's drawn out there. So we can look at what's inside that folder. So we've got a small sample here of some text files that she's been recorded containing sample data. And then there's a few programs here that we need to run on our GU data to do the analysis, which is what we'll be working on for working towards during the last of this morning's lecture. So we've got a few questions and exercises to see if we've understood what we've been teaching so far. So let's try talking about those. Is this readable? Yeah, we'll just look at the figure and then I'll make it a little bigger. So the idea is that we've got this file system that, like I've shown, starts with users, and there are two users, thing and backup, and they contain some folders. Confusingly, some of the names are the same. And then we are asked, let's just make this one bigger. If pwd displays user thing, what will ls double that dot slash backup display. So, does anyone want to venture a guess on one of these 4 options? Will it show double dash backup, no such file or directory, aka it doesn't exist? Will it show these lists of things starting with 2012, 2013, and 2013? Will it show them with slashes on, or will it show original, pnas final, and pnas underscore sub? So
where are you at to begin with?
So to begin with, we are in users thing
Okay.
here. Then we do ls double dot slash backup. So the question, the basic question is, where will that take us?
You'll see original and you'll see those two.
Yeah, exactly. Because we're doing double dash, which takes us back up into users, and then slash backup, which takes us down into this backup folder, and not into that backup folder. So that's the important thing, and why stuff like PWD is useful. Because you can very easily come into the situation that you've got several different folders with the same name. For instance, here I've got my users folder, and we've got the users folders inside null. So it's important that we keep track of that these are 2 different things with the same name that are only separated by their place in the file hierarchy. So if we are inside users backup, and we're told that putting an ls, a hyphen r on our ls command displays things in reverse order, what will we see when we do, which command will then print pnas sub, pnas final, and original in that order? Any guess?
So raise up your little red stick instead of raising your hand.
Yeah.
So, that way we can.
Yeah, so anyone want to come venture a guess on which command we need to run? lspwd, ls/rf, ls/rf users backup, or either of number 2 or 3, but not number 1.
Either to the slash.
Yes, because number 1 is missing the R flag, so they will come in the opposite order. This one will work because we're already in the right directory. And that one works because we tell it to start in the right directory, which happens to be the same as the one we are in. So these are 2 different ways of doing the same, either by relative path, aka nothing because we're already there, or by absolute path because we start with a slash. Does that make sense? I think so. So what does CD do if we don't put anything after it? That's probably fairly hard to guess if you don't know. So we could try it out. So if I do CD and then nothing, and then PWD, it puts me back into my home directory. So that's a shortcut. When you've navigated to somewhere that you don't want to be on your computer, then you just quickly want to get back to your home directory, then you can just do CD, and it takes you right back there. Yeah. So the other important thing about home directories, which we'll revisit again, is you may have noticed that what's printed before my username, so this has format of some name, colon, something, and then my username. So in this case, the first thing is the name of my computer, and then after the colon is the directory that we're currently in, and then the username. You can customize this prompt, but that's a bit more advanced than what we'll be working on in the first instance today. But it displays your home, the directory that you're currently in here. So if you do cd and nothing, then it displays a tilde. And the tilde is an almost universal shortcut for your home directory. So you can achieve the same thing by typing cd tilde, and you can do cd tilde slash some directory inside your home directory to quickly navigate to that place. So that can come in handy in quite a lot of places.
I just have a question.
Yeah, sure.
I'd like to be able to see the tree structure that you're seeing. I don't have it on my terminal, and I don't know how you're looking at it.
You mean in the prompt here?
No, the tree structure that we were referring to
The
earlier.
exercise?
You know, the exercise that showed.
I think that was hypothetical.
Yeah, so the one that showed thing and backup is just something that's made up in a drawing. The one we should have is the one that shows users, Nell, Larry, Imhotep. So this one. Yeah. Yeah, sorry if that wasn't clear. So that came from following this link, and then we're working our way through the topics. So we are in the files and directories tutorial, and we were looking at the exercises questions towards the bottom of this one. So this diagram is there. In general, almost all we say in this session, at least today, should be available via this link, and via this link from the main software carpentry side of today. So the link is here, and those pages will stay up for reference if you want to use them. It might also come in handy here. So we've been working our way through topic number 2 now. There's a reference file here which may come in handy that contains introduction to what all these commands, short explanation of all the commands that we're using, and some more commands that we won't have time to cover are doing. So that's a basic reference that's probably useful. So follow the link here from the shell side to references, and then you can have that open in a tab in the background as something you can look up and use.
And now I need to get rid of this, and I'm trying to get rid of that. Okay, so how do I get to that link?
So you use everything from
Yeah, right there.
so it's begin here in the show.
Exactly.
Yeah. And from here, there's a few links, so
Right.
the one that we were just at was files and directories.
So are we ready? Are people happy to move on with doing something more? Think so?
Should have put up my reach.
Yeah.
There was a last question on that list that you had, like one that's.
Oh, I think maybe there was one we skipped. We can do that one. So this asks, what does ls do when we use it together with s and h arguments? So we can try it out and see what happens if we do ls/s. So that prints a 0. It's maybe a bit hard to guess what that 0 means, but let's try moving somewhere where we actually have got files and try it again. So it's clearly got something to do with that. The canonical reference, so if you want help with what these commands are man pages, which you access by typing man and then the name the command. So that tells us something about ls that probably doesn't work if you're on a Windows machine with git bash. So the alternative is, one of the alternatives that you can use is to simply Google it. And you'll find the same, more or less the same text. You can also use the reference, of course, inside that we just talked about, which explains some of it. But anyway, if we read this manual, it contains a lot of text, but we're looking for what /s is doing.
How are you scrolling?
So I'm just pressing the key down here to scroll. Yeah, so /s is displaying, it has got something to do with the size of the file, but it's rather arcane in that it's in the units of 250, 212 bytes, or 512 bytes. So that's not overly useful. You can use the /S, which sorts by file size, which is maybe more interesting, which will then sort things differently from just doing ls. The other thing that we were asked about was /h. Yeah, it may be. Let's look at the man page. So we scroll down again. So there's obviously one might wonder, how are you ever going to memorize all of these options to ls? And typically you don't. There's a few of them that you find useful and you will memorize. If you need them, then you will use the man pages or you will Google to find if there are more options that you need for something special that we rarely use because yeah, so -h is in this case used to get sizes which are in bytes, kilobytes, megabytes, and gigabytes, and terabytes, and so on, rather than just showing a huge number. But it only works when you're actually using it together with the /l option, which we didn't try. So /l is printing it as a list, which shows apart from what we already had, then it showed when the file was last modified, it shows who owns the files, then it shows something about permissions that we're not going to use, which is a bit above the level that we're going to consider today. This D shows that it's a directory, and then this thing is the actual size of the file in number of bytes. But obviously, to figure out exactly what that is, you'd have to manually divide by 1,000 and so on. So it's probably easier to read if you do like this, where it shows that it's where it actually uses the suffixes. So we can see that that file is 21 kilobytes. That one is 32 bytes. That one is 202 bytes, and so on.
So it sort of gives like the units.
Yeah. So instead of just showing the number of the size in bytes, then it shows the size in bytes or kilobytes or gigabytes, according to what's appropriate for the given file size, which makes it humanly readable. So that's the idea, that the H is indeed for humanly readable. Right. So we've played around with how we can navigate. We've seen that we can see the contents of the file. Now we've also seen how we can tell how big they are. We've also seen that we can tell when they were last modified, and so on. But all of this so far has been about watching stuff. We haven't actually created any files or modified any files or directories for that matter. So that's next up. Imagine that we want to start working on the thesis. So the first thing to do is to create a directory that we put that into. So if we use the command mkdir for make directory, and then the name of the directory that we want to make, we can see that currently we haven't got a directory by that name. So we do that. We do ls/f again. And now there's a new directory here. We can use the /l to see that that directory was indeed created 10 minutes past 9 on the 6th of July. And then we can navigate into that new directory that we've just created, which is naturally empty since we just created it. Now, the next thing is, of course, that we want to be able to modify some files. And to do that, we're going to use a text editor. There are several different possible text editors that you can use. For this, we're going to focus on using Nano, which is a simple, reasonably powerful, and for a terminal text editor, fairly easy to use. So that's the one that so if we do Nano, and then name of a text file, press enter, then it will open the program called Nano, and it will be modifying a file called draft.txt. And if we just start typing, then we can type some code, some text in there. Then all the stuff down here are shortcuts that we can use. This syntax is short for control and then the letter after it. So to exit, you would press Control X, and it asks you, do you want to save your modified file, yes or no, or Control T to cancel, and so on. There are several other options down there, obviously, but the main thing we're interested in for now is that we can open a file, we can write some text in it, we can exit, and we can save the file. Then we can use, to view what's actually inside the file we've created, we can use the command cat draft, which will just basically print out the contents of that file. Yeah, everybody, let's have a go at making sure that you can open and modify a text file with Nano. And when you're happy with that, then I'm not actually sure. Let's see if anyone. Yeah, I guess so. Yeah, you can actually use it to join things together. A lot of these names are very cryptical, and they are basically puns on various things that were. So the reason that the text editor is called Nano is that there was another text editor called Pico, and then they thought that was funny to use a different prefix. So those names generally don't make a whole lot of sense, but unless you know your Unix history very well. Yeah, put up a green sticky note if you can edit a file and save it and cat it. One danger here is that if you accidentally get another text editor open, you might end up inside Vim or VI, which is a very powerful but somewhat complicated text editor that you probably would like. So to get out of that one, you have to type Control Q. Generally, commands in that one are colon Q to quit. But for now, we'll focus on Nano, which is somewhat more naturally user-friendly. So Nano will of course also be able to modify a text file that you've already got by typing Nano and the name of the file. It won't create a new file, but actually open the existing file and modify that one. No, I mainly talked about Vim because it quite often happens that Vim is the default text editor, and if you just if someone tries to modify a file for you or open a text edit for you, then it will typically open Vim, and if you don't know anything about it, then you can't even figure out how to exit it because there's no user interface visible.
Do any window keep?
I'll put a note in the Etherpad.
Yeah, oh, great.
I think it's under the bash part.
Yeah.
There's a link to this software Carpentry Windows installer, which installs Nano and a couple of other things that make the Git bash behave a little bit more like normal, or not normal bash, but
But bash on Windows, on Linux and Mac, yeah. All right, I think we are ready to move on. So we've seen that we created that file. And we can use LH/LH again to see that we've created this file, and it's 44 bytes large, which is probably roughly the number of characters that we put into it, since it's just a text file, when it was last modified, and so on. So the next thing is, now we've created a file, now we want to be able to get rid of it again. So the command for removing files is called rm for remove, and then you can remove the file. So if we do rm draft, then the file is gone. And I'm warning about this thing, it's not as a graphical user interface thing where the file that you remove goes into a trash bin. This is a proper removal of the file. You may be able to recover the things from disk, but the file is really removed. It's not moved anywhere. It's removed. So be careful with what you do with commands like rm. The next thing we might want to consider is removing the directory. So say that we actually don't want this directory thesis anymore. So we do rm thesis, and we're told we can't do that because it's a directory. So there's another command for removing directories, which is called rmdir. If you try doing that, then it will tell you that you can't remove the directory because it's not empty. So you can start by removing the file, and then you can remove the directory.
I continue to have a hard time staying inside the wrong shell. I think I'm fighting this problem. Am I in the right place?
And then I'm just going to recreate the directory.
I'm getting what he's teaching. This is fair, but I'm not getting.
The second option for removing a directory which contains files is using rm again, but using the flag recursive. So this R in rm stands for recursive, meaning that it first goes into the directory, removes everything in there, then goes up a level, and then removes the directory. That works, and that just removes the directory. Obviously, that command is fairly dangerous. Because if you use that on your home directory, then you remove all of it, and then you lose all your files, so be careful.
I will say that on any machine I do, the first thing I do is alias rm to be interactive, so that's like the -I option, and that asks you, are you sure you want to delete this before it deletes it? And you can force that if you have like 100 folders, you don't want to deal with those. There's a way to get around it, so it's not asking you for every 100 items, but just for me, I'd rather be safe and have it ask me than accidentally delete my thesis, say.
Yeah.
And tomorrow, when we learn version control, you'll learn how to recover it. But it's still, you can do a lot of damage very quickly with RM.
Yeah, it's really, and especially the things that you need to be careful about is if you start, we'll show you how you can use wildcards later, which is a way of completing file names, and then you can really basically remove everything with one command that you ran. The other thing is, if you use rm/r from somewhere and you didn't realize that you were in a different directory than what you thought, you might also create damage. So again, PWD to make sure that you are where you expect to be is really useful. I will recreate the thesis directory again so that we can right. So now we've seen how we can create files and how we can remove them, but it may be that we're also actually just interested in moving them around and renaming them. So to do that, we want to use the move command, which is simply called mv. So we can do me thesis. So let's say that we actually decided that that this text file doesn't contain the draft of the thesis, but it rather contains the introduction to the thesis. So if we run that command, then move a name of an existing file, and then the name of a file we want to move it to.
Oh, sorry.
And now we've indeed changed that file. So we just moved the contents of draft into intro.txt. Move can do two things, so it can rename a file, but it can also move a file from one directory to another. So we could say we wanted to move that file from the thesis directory to another directory. Then we can do that. We've seen how double dot is a shortcut for the directory just above where you are. But dot is actually a shortcut for the directory that you're currently in. So if we do move thesis intro.txt and dot, and remember we're now in the directory just above this one, and we do ls, then we can see that we've moved intro into here. And if we do ls thesis, then that directory is empty because we moved the file out of there. So those two different concepts of moving things with the same file, whether or not if you put a directory as the second command here, then it's going to move the file into that directory. But if you put a file name there, then it's going to change the file name. So those two things are very similar but subtly different. Yeah, play around with moving some files around until you're happy that that works as expected, and then put up a green note again. Right. It looks like we're a few people short, so we'll just wait a few minutes. We'll have a break in roughly an hour, which is a bit longer, but yeah, feel free to pop out and get something to drink or stretch your legs. We'll just wait with starting up again until we're a bit fewer people short. Yeah. So now we've seen how we can move files around, how we can remove them. The last thing we need to actually manage files is to be able to copy the files. And indeed, there's a command for that, which is called CP. So we can copy our intro file back into the thesis directory. So if we do cp intro.txt, then we're copying the file intro.txt into the thesis directory. Just as a reminder, if we want to inspect what's inside the thesis directory, then we can use ls and then giving it the name of the directory that we want to see the contents of. So again, without moving, we can see that there's now an intro.txt inside the thesis directory. And there's also an intro.txt where we currently are. If we remove the intro.txt file, which is in our current directory, then that file is gone. But if we do ls thesis, then it still exists within the thesis directory. So we've created a copy of the file, and then we removed one of them. So effectively, that's doing the same as move is doing. But typically, if you want to move a file, then move is much more suitable than copying and creating. But for some reasons, you may want to have a copy of your files, and then cp is the command you want to use. Yeah. There are some more questions that we can look at. Let's do that. Yeah, so we're creating a text file. We just managed to make a typo in our statistics file.txt, so we want to rename it. Which command do we want to execute? CP statistics.txt, move statistics to statistics.txt, move dot or copy dot. Which of these commands will do what we want? Anyone want to enter, I guess? Yeah. Yeah. So number one will indeed also create the file, but confusingly it will leave around the other one, so there's no good reason to leave around a file with a typo in. Number 3 and 4 can hardly do anything right, because you're not telling it what you want to, you're just telling it which directory you want to move it to. So it should, if that would ever work, then it should be able to read your mind about what the file should be called. So those are unlikely to work. They're just moving us around, moving the file to a directory. And actually it's moving a directory from the one that it's already in to the one where it's already in, so it doesn't do anything. And the fourth one copies the file from where it is to the same place. It also doesn't do anything. So imagine that we're standing in the data directory of Jamie's home folder. We do ls, that contains a file called proteins.dat, which is presumably some measurements is done. We make a directory called recombine, and then move proteins recombine, and copy recombine proteins double dot proteins that's saved, and then we do ls. So what will that contain if we do ls in the data directory? See if there's anyone else. So it could be 1. 1 is certainly correct in that there's the recombined directory. So it can't be number 4 because that doesn't contain the recombined directory. But we're actually, when we're doing the copy here, we're not copying it to proteins saved, but we're copying it to double dot proteins saved So that file will actually be created in users Jamie proteins saved, so we won't see it when we do ls. So the right one must be number 2, because number 3 is excluded by the fact that the file which we moved is still there. Number 2 is the right answer here. So suppose we've got something here where we've got a couple of files, a raw directory and an analyzed directory. We want to end up in a situation where we moved everything to either the analyzed or the raw directory, and the analyzed, and if we do ls analyzed, then it should contain fructose and sucrose. So how could we do that? Yeah.
Move the data files into the analyzed folder.
Yeah, so you could do mv fructose in analyzed / and then move the other file and so on. So that would be the way of going about doing that.
Can you move them at the same time?
So we could try and see what happens. So let's create 2 text files. So now we do move intro.txt and draft.txt, and then we want to move them into the thesis. So let's see what happens if we try executing that command. It certainly did something. The files are gone. ls the thesis directory, and they're both in there. We can use cat to see what's in them, to just make sure that they contain what we expect. So, yes, move is clever enough that when you supply it with something which looks like this, a list of files, and then a directory at the end, then it will do the right thing. In the other case, say we haven't actually created a directory and we try to execute that, then it will be confused, because now it will actually try, when the last command is not a directory, then it will actually try to move the file. So if we do move intro into something which is a non-existing directory, then it doesn't create that directory. It creates a file called test, which is moved intro.txt into. So that version of the command, where the last argument we've given to it is not a directory, but a file name, can't work with 3 arguments, because it would have to move both files into the same file, which would either not be a move or destroy one of the files. So that just refuses to work. So it says move can be used in 2 ways with various flags. Source and target, which is in the case where you're moving a file from a file name into another file name, or move source / for more than one source file and then into a directory where the last argument is a directory. So that's what it's trying to tell you here in a very shorthand form. Yeah. And this question we've basically answered, because that's what we've been experimenting with now. So we are creating a directory called backup, and then we cp 2 files and backup, and that indeed does the same thing as what we've just shown that move does. So it copies both the files into that directory. So in that way, copy and move works exactly the same. Again, we can experiment with what happens if we try to copy several file names. And again, you get a similar output. In this case, copy takes somewhat more different arguments than move does, but again, it says you can either use it in the form where it's a source file and a target file, or multiple source files and a target directory. So in that way, we're fortunate that move and copy works the same way, and as we might expect, and are fairly flexible. So there are more arguments that we can use in ls. We can use /R to do recursive. So like we used rm/r to recursively delete, then ls/r recursively lists the contents of files. So say we want to show all nels files, then we can do ls/r, and it will print first all the contents of this file, then all the directories, the files inside those directories, the directories inside those directories with their files, and so on, so that we can inspect everything which is available. Then the question is, the command ls/t will sort things differently because it sorts things according to when it was last modified. Because we just created the thesis directory as we've been going on, then that is the first directory when we sort according to modification, where all the others were already existing files. So what do we think happens when we do ls/t/r, or the other way around, which probably amounts to the same thing? Anyone want to venture a guess about that? Recursive and
Oh, it's recursive, is that what the R is?
yeah, so the R is for recursive. It's going to print something like this. So we're doing something where we're sorting the directories according to the time of last modification, and then we are printing them recursively.
I think a lowercase r might be reversed, because I use that a lot.
Yeah. So we can check that when we do by doing man ls, or perhaps. Yeah, the other way of getting help is let's look at the man page. We are scrolling all the way through all of this to look for R. Yeah, so confusingly, yeah, capital R is recursive and lowercase r is reverse. And it's a bit unfortunate that these things are not always consistent across commands, because as we saw when we did rm, then here R, capital R and small r is actually the same thing. So these things are unfortunately not always consistent across commands, because these commands were grown organically as the need for different file system commands grew, and people haven't actually always fixed the syntax so that it's the same thing. So we will have to live with that. That's also why you might wonder why it's print work directory, but it's who am I, so there could be a where am I would be more natural match, but these commands have, yeah, the names are for historical reasons. Some of them are indeed, as we talked about earlier, puns on names of other commands like nano and Pico. So in this case, Pico actually doesn't exist anymore, so now it's just an alias for Nano, but that used to be a text editor before Nano, which was why they created a text editor with a different name. Yeah. But back to the actual ls/t/recursive. So it looks like it's actually doing mostly what you would expect. It starts with the thesis directory, which is the directory that was modified the earliest, the directory that we modified. And then it goes through the directories in the order where the directory has been modified. And then it goes through all the elements in there in the order that they've been modified. So does that make sense? I'm not sure that that command is overly useful. Yeah, great. So now we've covered the sort of basics of figuring out how to modify and move and create files and doing stuff with them. Now we're going to look at something which is a bit more powerful, of actually being able to use the shell to chain together and make it do several commands after each other and do really powerful stuff. So let's cd into the molecules directory of Nell's home directory, which contains some protein data bank files containing a few molecules that are apparently relevant for the research. Say we were somewhat interested in how big these files are, we can use the command wc for word count to actually count the length of these files. If we want to know all of them, then we can use a wildcard like this to actually word count the contents of all these files. So this means this star will match anything. So we will match all files that are something.pdb. And if we do this, yeah, we get a list like this. So some numbers, and then all the names of the files, and then the totals. So let's look at the man page for word count and see what it does. So it gives you word, line, character, and byte counts. So we can use, for instance, we can use /l to see how many lines there are in all these files, or /c to see how many characters, if that's the only thing that we're interested in. Yeah. So suppose we were interested in somehow scripting our way to figuring out which file in our directory actually contains the largest amount of lines. So we've already seen that we can do word count /l. This gives us the lines. Then we would like to sort this thing and we want to store it. We could, of course, grab the text somewhat and then copy paste it to somewhere, put it into a spreadsheet and work with it. But obviously that's not the kind of thing we are after. We're after using the shell to script this and be able to continue doing our analysis. So one extremely powerful thing that the shell can do is that it can redirect the input and output of commands. So this syntax means that whatever is printed out of running wc/l star.pdb is not displayed on the screen, but actually stored in a file called length.txt. So now I used cat to inspect the contents of that file. Yes? Oh. So that means that we can actually store the contents inside a file. Now the shell also comes with a command called sort that will enable us to sort the length of the files. So if we do sort /n length.txt, then it actually sorts this according to the numbers out there, which enables us to figure out which one is the shortest and which one is the longest.
What does my sign do?
Well, let's try without it. That's the next thing. So it looks like it's doing almost the same thing, but it's suddenly different. So the thing is that normally sort puts things into alphabetical order, whereas the /n tells that you actually want to sort according to numerical values. So you probably know that if you've got a bunch of files in a directory, one of them that's called something like 1 to 10, then 1 is sorted next to 10. So you've got 1, 10, 2, 3, 4, 5, 6, 7, 8, 9, because they're sorted alphabetically. So then you end up putting a 0 in front of all the small numbers to make sure that they're sorted alphabetically in the same way. And the /n exactly means that you don't have to put that 0 in there because you're sorting according to numbers and not according to the alphabetical orders of the numbers. So we can confirm that by, again, inspecting the man page. It's got a lot of options. Yeah, and this one says compare according to string numerical value. So that's not overly helpful, but it means that we're converting it to a number before sorting rather than sorting according to the string. And again, this one has also, interestingly enough, has a /r command for reverse, which is similar to what we discussed before for the other commands. So we could continue our attempt of actually sorting this thing. By sorting the input, so we're sorting whatever comes in length.txt, and then we're storing that into a new file called sorted length. And indeed, that looks like what we had before on the output. Now, if we want to we're just interested in the smallest of these files, the one we're interested in figuring out which file of these is the smallest one. We can use the command. We can use a command to pick out the first line of a file, which is called head. So if we do head /1 -1 sorted length, then it will print the very first line. If we do that -2, then it will print the first 2 lines, and so on. Similar, there's a command called tail, which will show the last line, and so on. Now we've created all of this by creating all these temporary files and then running commands on the temporary files, but there's actually a better way of doing this, avoiding the creation of all these temporary files that we're not really interested in. So if we use the vertical pipe character, so just a vertical line here rather than the redirection into a file, then that will actually produce that output and then use that as input for the next command. So we've actually avoided creating the sorted length text file here. And we can take that one step further. And using another pipe character to pipe the output of word count into sort, and then pipe the output of sort into head. Which then gives us the opportunity.
What's the dash L tag after PDB that you have there?
So
Or PDB?
this one, so that's actually telling it, word count can count the number of words, the number of characters, and this one is telling it that we're only interested in the number of lines. So if we did /c, then we got the number of characters. It's still the same file, but it's now 422 characters. Yeah. Let's have a play around with trying to get something like this working. You could experiment with replacing head with tail to figure out what's the last line. Now that doesn't give you the biggest molecule, so we will have to do something else to actually remove that line and then find the next last line. So a combination of head and tail should do that. So we could try experimenting with that and trying to get something like this working locally and see that you can pipe commands like this together. This is a simple example, but it should show why the shell is very powerful, because you can, with very few characters, chain together commands and build programs that use simple basic steps to do powerful stuff in combination. Yeah.
Are we going to create the scripts with all this? So
Yes.
just can run the scripts instead of
Yeah. So the idea is now we're figuring out how to write and what we want to do. And then when we end today, then we'll have this in a script. So you just execute the script and then you do all the analysis. Great. Yeah, green sticky note when you're happy with getting the concepts of piping, and then let's work with this for a few minutes.
So we could just get just the total number of lines.
There's a few illustrative figures in the lecture notes that may be of interest.
So it's everything that you type to this point is an input to that next thing. So normally when you say sort, you give it the file name, but you.
Yeah, so this illustrates what we've been talking about. For reference, how it goes to the shell, or it goes to a file, or it goes into another command. Right. Let's move on. Now we've done this on some simple files, so let's try to extend this to the actual data set that we're interested in analyzing. So we're going into the North Pacific directory here, and the data directory, which we've seen before, contains a bunch of data files and those two programs. So let's try inspecting them. So we're going to do basically the same analysis just to find the length of the text files. No, so we moved into this directory. So North Pacific 2012 -73.
Yeah, so go into CD.
Anyone having trouble finding that directory? Great. So we're trying to do the same thing and looking at the contents of these files and see what's going on. And again, we're using word count to find the number of lines, sorting it, looking at the 5 first ones. And we can use tail to look at the last 5 ones. So interestingly enough, there's one file that looks a bit out of place. All of them are 300 byte of 300 lines, except this one, which is only 240 lines. So that's a bit odd. So if we actually look, that file was 2018B. So we can look at that file, and then there's probably something wrong with that file. So we might want to exclude that file from our further analysis because it looks like the apparatus wasn't correctly configured or doing something else because it didn't take the same number of measurements as in all the other ones. So other interesting thing is that all the files are supposed to end with A and B. Then there's one here that ends with a Z. So let's look at if there are more of those. And indeed there are 2 of those files. So those also fall out of place, are also out of place compared to the rest of them. So we probably also want to exclude those from the further analysis because they're different kind of measurements according to the expected protocol. And there's a way that we can actually use ls to make sure to find all the files that have the right name. So they should end in either A or B. So if we use a syntax like this, then it means anything and then a character which is either A or B .txt. So the thing inside the brackets are matching either one of them. And that prints then the number of files. Now, if we want to count how many of these files there actually are, we could again use a pipe. So we could actually just pipe that to word count /l. So now I've used the list option to ls to get this printed as a list. And then I'm just piping the contents to word count /l. So that counts how many lines there are in this list. If I remove this .ab, then we get 17. So we're excluding 2 files by only looking at the ones that end in ab.txt. Does that make sense? You can see the combination of these 2 simple things, listing and word count, enables us to build something that can count the number of files with a certain characteristic using quite a few, not very many characters, just because we can actually pipe the output from one command into another. Yeah, there's a few more tutorial questions that we can look at. So we talked about this already with the sort command. That if we sorted an input like this, then it actually gets sorted into something like this. Because what happens is that it's sorting according to the order of the first character and then according to the second character. But that's not the typical numerical sorting we actually want. We want to sort according to the size of the number. And that's what we get when we do /n. Which is, I don't really know how much there is to explain about that because that's what it's supposed to do.
What if you use -n and you don't have a number in the line?
Well, I don't know. Let's try it out. So let's go back to our thesis. So now it's sorting alphabetically. And it's apparently still doing that. So that's actually,
Okay,
So-
if you had, if there was a number, I mean, if there was one line that had a number in it. that's
yeah,
number four,
let's see if we can figure it out.
I assume it'd be, these would be before, but I don't know.
No. So,
So it's like 0.
yeah. So that the question is, the answer is probably rather that you want to avoid doing that. For most modern commands, you would probably expect this kind of thing to fail and give an error rather than silently doing something unpredictable. But many of these tools are somewhat older. We'll see in the Python session, we'll probably see something about that it's often beneficial for things to error out rather than doing something weird when you've got some input that doesn't really make sense. Do anyone happen to know what sort is supposed to do when there's not a numerical input? The manual page is obviously rather vague on that. So it just says compare according to string's numerical value. So you have to know how it converts it to a numerical value when it's not a numerical. We can probably look that up, but let's move on for now. The other interesting thing is that we saw how we could use a bracket to pipe output into a text file, but we can actually also use a bracket, the other bracket, to pipe input into a command. So we could type something like this, word count /l bracket my data .dat, which actually doesn't tell word count /l to read the file my data.dat, but actually pipes the contents of that file into word count. So these two things are subtly different in that this one reads the file and then puts the output in, whereas this one gives the name of the file and lets word count open that file. So let's try experimenting with that. So if we just do word count /l like this, then it doesn't do nothing. It actually stops and waits for your input. So if I start typing, then I've typed 2 lines of text. Why doesn't that work? And then I press Control D to actually terminate. Then it counts the number of lines that I've typed in. So when you don't supply a line argument, a file argument to word count, then it starts word counting on whatever you're typing. And you can terminate with Control D. So this was 4 lines in this case. So what happens when you do like this, then rather than waiting for you to enter some input, then it actually reads the input from the file, and then it does exactly the same thing as I just did. And counting the number of lines in that standard input. Whereas this counts the number of lines in the file. File is called test. So that counts the number of lines in two files. Do people see the difference between those two things? The fact that you can do this means that even if you've got a program, even if word count wasn't written to be able to read files itself, then you can make it read file, then you can pipe the contents of a file into it by using this pipe character. So you can actually use programs that were not designed to read files on the content of a file without having to copy paste it, which is also powerful. Perhaps not as powerful as being able to pipe the output, but still quite useful. Yeah, and then the next thing is there's actually a double pipe character here. So let's try experimenting with whether you can figure out what the difference is between those two things. So if we try to do, so echo hello just prints hello. So that means that we will actually, efficiently what we're doing is that we're putting hello into those files, but in two subtly different ways that we try to figure out what's going on. So let's try that and see if anyone has a bet on what's going on. You may want to execute the same command several times in a row to figure out what's going on. Remember, you can use cat to see what's inside the file. Anyone want to bet on what's going on? If you try executing this, yeah.
Was it pending?
Yeah. So now we've executed the second command twice. So that does indeed contain two versions. Whereas if we, I used less here, but that's basically the same thing as cat. So if we do that, we can see that there are two files in here, two lines in that file, sorry. If we do the same thing several times in a row for file 1, it still only contains one line. So if you pipe into an existing file, you're just going to override it when you use a single redirection character. But if you use two, then you can append to it, which may or may not be. Both things can be useful depending on exactly what you're trying to do. So we want to find the tree lines, the tree files which has the least number of lines. Which of these commands would work? So word count, they're all using word count as we've been doing. Then these three are piping it with a pipe character. This one is redirecting it. And then using various combinations of head and sort. Anyone want to venture a guess on one that would work? Yeah, so number 4 looks right, because that's the syntax that we've always been using, with taking 3 characters out. This one is definitely the wrong way around, because we're cutting out the first 3, and then we're just sorting. We're cutting randomly according to the name, the first 3, and then we're sorting those, so we're not getting the smallest one. We're getting the sorted of the 3 version of the 3 first ones in the alphabetic order. The first one is just wrong because that's going to put it into a file called sort, and then something else is going on, so that's going to end badly and be very confusing. This one is interesting. We haven't actually looked at whether that syntax works, so let's try it out. So that doesn't work because this is not a valid command that you can say, you can give to head. Head and tail are very basic in the way that they take the first files. There's no way of using those commands to just take line 5 to 17, but you can combine head and tail by first taking off the first 4 lines and then taking the next lines if you want a subsection of the file to be cut out. So that's the way you typically go about doing it, with a combination of head and tail if you want something in the middle of the file. Yeah, then there's an interesting command that we haven't used, which is called unique, which may come in handy, which can take a file, which could contain lines like this, and then remove duplicate entries that are right next to each other. Interestingly, it produces something like this, so it doesn't actually remove all the duplicates, but only the ones that are right next to each other. And the question is, why is that? So there are probably 2 answers to that. Anyone want to say? So they're hinting that it's probably something to do with what happens if you use very large files. So what happens efficiently, if you just want to remove lines that are right next to each other that are identical, then you can just take for every single line, look at this, say, is the next line the same as my line, then remove my line, and then go on. If you actually had to do all duplicates within the file, then you would have to take for every single line, look at all other lines, and then from the next line, look at all other lines, meaning that this will be n to the second power, where n is the number of lines. So that could quickly be a very slow command if you have a huge file with a lot of lines in. Whereas doing it only with the next one is only order of the number of lines. Also, the other thing is that the typical design philosophy for Unix command is to do one thing and do one thing well. And unique is very good at removing stuff that's right next to it. But if you want to remove all of them, then you have to sort it beforehand. And sort is very good at doing sorting. And it's very easy to pipe things together. So you can just sort the file and then use unique on the sorted file, and then you've achieved the thing without having to build a sort command into unique, which is what you would have to do to make it efficient. So that's quite typical why you see these Unix commands that are extremely basic. That's because they are meant to do one thing and do one thing well, and then you've got the pipe characters that enables you to chain them together and quickly build programs that do more advanced things, tailored at exactly your needs. Right, so we're trying to figure out what happens if we run this command on the contents of this file containing the following data. So we're catting it, then we're using head to take the first 5 lines, then tail, and then sorting. So anyone want to walk us through? Let's try walking through the first steps. So what happens first is that we do head, so we get the first 5 lines. Just be something like that. Then we do tail, get the last 3 lines. We must end up in something like that. And then we sort them.
But we sort them backwards?
We sort them, yeah, so the thing is that we sort them with reverse. In this case, the R is for reverse. And then we put it into final. So, yeah, so that should put them in reverse alphabetical order. Yeah.
So when you do head, it's deer, rabbit, raccoon, rabbit, deer. And then when you do tail, is it deer, rabbit, raccoon, or is it raccoon, deer?
So they will still, so the question is whether they are reversed when you do tail right. So tail will still print them in the same order. It will just take the last 3 ones. Could do the other thing, but it's not. Typically tail is very often used when you've got, say, you've got a log file, so you've got something, some program that's been running for hours and hours and does something, and then it writes to a file, and you want to figure out how far has it gotten. So you just want to look at, that file may be very large, so you don't want to open the full file in a text editor and scroll all the way to the bottom to see what it's doing now. You just want to see the last 10 lines. So that's a typical use case of tail. And there's even a follow option to tail, which is quite useful, which means if you've got some program, some analysis program that's writing output to a text file and you want to have a terminal where you monitor the progress of that, then you can do tail/tail-f on that file, and then it will automatically update as the contents of the file gets written. And you can keep track of what it's doing. Yeah, so then we're using the command cut, which we haven't seen before, but which actually cuts out from the comma character and then onwards in our animals file. So we get rid of the dates. These are presumably sightings of animals on some specific date, and we get all this, and we get that contents. Now we're interested in which animal names are in the file, so we've managed to cut out only the animal names, and we want to figure out which names are in there, not how many times, but just which unique names are in there. How would we go about doing that with using commands that we've already been using?
You could use you could sort it and do unique.
Yeah, exactly. We want to do first sort and then unique, so that we sort them so we're sure that all duplicates are next to each other, and then we do unique to remove all duplicates, and then we've got the unique list of names. Exactly. Right, I think we're scheduled for a bit longer break now at 5:30, so let's take that one.
How long?
What's in the plan? Let me just check, because I can't actually.
It doesn't look like they're supposed to like refresh the food outside. It doesn't look like they have yet. 2 minutes. Come back. It's 10 o'clock.
Yeah.
Not bad. It's 10:45-ish.
Yeah, sounds good. Then we will see. We will crack on with using loops and trying to complete our analysis of this program. Let's get started again. So we've now looked at doing the piping. There might be situations where we need to do the same thing over and over again for several files. As we've talked about, then the goal of this example is being able to do analysis on a whole bunch of different text files using a pipeline that we're putting together. So to do that, we're going to look at using loops to run over the same command again and again with small variations. We're going to see that again when we do the Python after this, how we're going about doing it in Python. But for now, we'll look at doing loops in Bash in shell scripts. So one example of a place where we could need to use loops would be, so we're now entering the creatures directory of Null's home directory, which contains 2 very real creatures data files. So now I'm using a command called less instead of cat, which is basically the same, apart from the fact that you can scroll up and down with the arrow keys, and you use Q to quit. And you can see there the basilisk file contains name of the creature, and then it apparently contains some DNA structure and some metadata, and probably the same for the unicorn. Yeah. So say we wanted to move those files So we want to rename them to something which starts with original. It would be neat if we could just do something like this. So we take some file name .dat and then we rename it to some other file name original hyphen the same thing .dat. Unfortunately, that doesn't work because this is not a loop. It's actually completing the star to all possible matches, and then it can't figure out. The shell is not smart enough to realize that you want to complete this into two different move commands, where you first move basilisk to original basilisk and then unicorn to original unicorn, because it's completing this into one command. So the way we want to go about doing this is that we want to say for each creature, move this to a different file and then repeat for the next creature until we're done with all. And we can do that with a for loop. So the syntax for doing that is for some name in, and then the list of things that we want to run over, that we want to iterate over. So in this case, we're iterating over those two files, basilisk.dat and unicorn.dat, with a variable called file name. If we press enter now, then you can see that the shell has changed. So we used to have this computer name, blah, blah, $, and now the shell just shows you the pipe key here. So that means that it's waiting for more input, because I've started a for loop, but I haven't actually ended it yet. So it's waiting for input until I end this for loop. The syntax in Bash is that you write for this, then you have to write do, and then what you want to do with these things. So we can, for instance, do head -3 to print the first 3 line. Then we call the variable up here file name. The way you access a variable, we'll show how this works in Python later on. But the way you tell the shell that this is a variable is by using the $sign here. So this is not the text file name, but the variable file name that we're referring to, because we're using the $sign here. And then we end the for loop by printing done. So for some variable name in a list of possible in a list, then you do something, and the thing you do is head -3 of that file name, and then you're done. So that prints first the 3 lines of the basilisk files, and then the 3 first lines of the unicorn file. So let's see if we can get that working and put up a green sticky note once we've got that. Yeah, to clarify a few of these things, we can show that we can actually change file name. So I haven't really shown, but you've probably seen by now that if you press your up button, then you get the last command that you typed in. In this case, that was my for loop. The way that Bash represents the fact that this is multi-line is by, when you go into your history by pressing up, is by using a colon wherever there's a new line, rather than printing the new line. So the new line has been replaced by the colon. So let's try playing this around to this. So we called this file name, but we could actually just call it F or something else. So I've created a variable here, F, that I'm looping over, and then I'm putting the value of that thing in down here. So that does exactly the same thing. File name, or F, is just a name of something that we can call anything. File name happens to be a good variable name because it tells us what it is that we expect this variable to contain. But it's just a name. if we actually wanted to do the thing that we set up trying to do, so remember that we tried doing move up here, where we wanted to rename all the files to start with original. Then rather than doing the head thing that we were doing in here, we could replace it with move. So now I'm moving. File name will first be basilisk, so I'm doing move basilisk to original basilisk, and then I'm doing move unicorn to original unicorn. And then it doesn't work because I've got one variable here too many. So now I've moved them. We could also imagine that we had a large amount of dat files, then it gets tedious to have to write that we wanted to do something with all of them, then it gets tedious to have to write the list of all of them here. So we can also use a wildcard here and do something like this. So this matches star.dat will match all possible dat files. So even though they're not called basilisk and unicorn, but original basilisk and original unicorn now, then it works. If I try doing this, then I'll be told that there's no such file because I just moved it. But using this format, then it will match all the dat files in there, so it will still work. Yeah, we can even make it a little bit more explicit by adding another line in here. So remember that echo just prints what we put after it. So if we write something like this, do echo file name head -3 file name with a semicolon after that, and then we put 2 lines into our for loop now, where the first one just prints the name of the variable. So we can see the first file is called original basilisk.dat, and that contains those 3 first lines. Then the original unicorn file contains those 3 lines, and so on.
I haven't used this for loop in Bash.
Mm-hmm.
The do, why do we have to use
The do.
the do?
Yeah, the syntax, compared to the syntax in Python or other modern languages, then the syntax seems a bit verbose, and the do seems a bit unnecessary. And that's a legacy of it being an older language, I would say. It's
You can think of the do and the done as kind of bracketing
Yeah.
what's supposed to be done to each file.
Okay.
mostly in other programming languages, and then you've chosen to bracket things by the for and the end of the loop, whether that's unindenting as it is in Python, or it's an end for or something like that. But yeah, you would probably see as you start working more in Bash, and when we're talking about Python, we'll talk more about that, then there comes a time when you have to do more and more complicated things where doing them in Bash is cumbersome and the syntax seems too complicated, and you're typically better off writing a script in Python that does that part of it, and then leaving the Bash script to do the relatively simple things, because Python is a more powerful programming language for doing things in, and has a nicer and more friendly syntax. But many of the concepts are the same. So imagine that we've always been working with files that don't contain space. So now I've created a file that happens to contain a space in there. So this is a bit of a tricky thing than when you have to write this kind of thing to get it right. So if we just try to run our loop as we wrote it before, for file name in star.dat, remembering that we created the red dragon.dat file, do echo, so we print the file name, and then head of the file name, and then done. If we execute that, the first two ones still work. The next file name is red dragon. But then it actually gets confused because head gets two arguments, one red and one dragon.dat, and neither of those are existing files. So it errors out with no file or a directory with this name, and the same thing again when trying to open dragon. And that's because efficiently what we're doing inside the for loop is this thing where head interprets red and dragon as two different things because it uses space as a separator. So even if the space is inside the file name, then that doesn't match. So one way of going about fixing that is to quote the variable. So if we put quotes around it, then we tell the bash script that this is actually one thing. This is one file name and not two different ones. The other thing is the other way is what you could see that the bash completion was doing before. So I started typing red and pressed tab. Then it puts a slash in there, which means this is a space, but it's a space that's been escaped, as they call it. So the space is not to be interpreted as a separator, but as a part of the file name. In general, in almost all cases, then avoid spaces in file names, and then your life will be much easier when you have to deal with them in a shell script. But these are the ways around it. So we could go about fixing that here by making sure that we are quoting the variable name here. And then it works again. So I just added quotes inside our for loop around the file name when giving the file name to head to ensure that the full file name is given to head. Another neat trick is, say that you want to write something like this, but you want to do the move. So we want to move something. But we're not actually sure that the command that we're doing is completely correct. So we want to ensure that this is getting done correctly. So one way of doing that is adding an echo in front. So remembering echo just prints stuff that's following after it. So now we can see what's actually going to be done when we're executing it. So what will happen when we're running this for loop is that 3 commands would be run. Move original basilisk to new original basilisk. By the way, these file names are terrible, and we'll show you in the version control session why and how and what to do instead of creating new original that reversed and so on. But
My program 3 final.
yes, exactly. So this is an illustration of what not to do. Because even though you always think you're creating the final version of some file, then you will always end up in a situation where you still have to make one final modification after you've done your final file, and so on. So that's one of the problems that version control will solve, and we'll be working on that. Yeah, so now we've seen a little bit about how the for loops work, so let's go back to actually doing some analysis on Null's pipeline data, on Null's measurements data. So we go into the North Pacific directory again. And again, we remember that we wanted to look at all files that ended with /ab.txt, because we figured out that there were these .z files there was something wrong with, which weren't the right type of measurements. So if we do for data file in *ab, then we get one of those files that are ending in either a.txt or b.txt, which is exactly the ones that we want. And I, of course, have to put an in there. So that's the syntax for variable name in, and then the list of things we want to match. And then again, the do. Yes. Right, you are. So now I've just typed do and then again echo to just make sure that we're printing out the right variable names. And then perhaps we want a statistics file with the statistics extracted from that data file. That's called stats, and then the name of the data file again, so that they're completely matched. And we can see that those files look as we expect. If we go down through the list, we've got all of these. And there's no one containing any C's in there, so that looks about right. Remembered from earlier, there were supposed to be 15 files, so we can verify that there are also 15 lines in this output by piping it to word count /L as we did before. So we just double checking that we're doing the thing that we expect to, and then we're indeed still processing 15 data files. So our *ab.txt still matches the same 15 files as it did the last time we were looking at it. So it looks like this is about what we want to do. Now we actually want to do something with the data files. So Nell has got a couple of different programs that she wants to run on the data files. One of them is called GooStats, and the other one is called GooDiff. So we want to actually be able to execute GooStats on all of these files. So if we do, the way we want to run that is to do bash GooStats. So that tells the terminal that GooStats is a program they want to run, and we want to use bash to run that program, and then we want to run it on one of our data files, and then we want to output that into some other file. So if we want something like this, that takes a few seconds, and then it writes it to the output. So that writes some data to the output file. Now we could go back doing that manually for every single file, but obviously that's the thing we want to avoid, because this is really tedious when it takes 2 seconds and we have to redo it. It would be much nicer if we could do it in a loop where the computer automatically continued when it was done with the first file. So that's what we want to do. We want to replace the echo with actually doing something. So we do the thing we just did before. Bash, calling GooStats, and then the file, and then the stats output file, and then we're done. And we just removed the word count that we had in here because we're not interested in that anymore. And we actually wanted to do goostats and not goodiff. So now we're running this command. Unfortunately, we can't really see what's going on. We're just waiting and hoping that this will eventually finish. It's a bit tedious, so we can stop this and do something more clever. So if I press Control C, then I break this loop and stop the execution. So it would be neat if there was a way to track the progress of this. One way of doing that is adding another line. So remember that we echoed stuff out before. So if we added a line here that for each analyzed files echoes out the file name, then we can keep track of how the analysis is going. So now we can see how it's going through each individual file, automatically continuing with the next one, doing the analysis. And now we're running this through 15 files, so that would be manageable to do manually, but imagine you had to do it through a couple of hundred files and every one of them take a couple of seconds. Yeah, that's probably a bit unfortunate that it's now running that on the stats files. That's because we already created the stats files, so we should probably have been a bit more clever. We can start by, so when we actually write a production script, then we probably want to make sure that the pattern we're using is not matching the stats, or that there are no stats files in there before we start. Because otherwise we're going to create stats files, which is obviously not what we want. Let's get rid of that output file as well, which was just some temporary stuff. Yeah, and we've sort of been using the terminal to interactively figuring out what we're doing and playing around with it. And we've been using the up and down arrows to navigate and go back and modify commands. Another way of looking at the things we've done is the history output. So history here will tell us all the last commands that's been executed. And that can come in handy because that means that when we've actually figured out what we want to run, then we can use history, and then we can go in and grab all those commands and copy paste them into a text file and and change this to be a script that we can actually run again and again and repeat this process, which is the next thing we'll focus on, actually to be able to write this into a script so that we can redo our analysis. Yeah, should we just spend a little bit? Have people got for loops running that can do this analysis? Otherwise, we should probably just spend a few minutes trying to get something like this running locally. Put up a green sticky note if you're already done with that and want to move on. Or if you're already done, then you can have a look at the questions which are attached to this topic, which are down here at the bottom of the loops section. Okay, in the interest of time and actually finishing this off, I think we will continue and going a little bit further with this, if that's all right.
So, what is the bootstrap? I mean, I don't understand what you mean by that.
What? Sorry?
The bootstrap? What is the process that we've been going through? I mean, what is...
So goostat is some program that calculates the statistics of that data file.
What's that?
So the data file contains some measurements, and say you want to find the mean and the standard derivation of that data series. Then GooseStat is a program that knows how to do that for this type of measurements.
But so GooseStats is just like an example program that's
Doesn't-
in this folder, like doing some specific analysis for this data. Like that's the GooseStats isn't something that you'll use anywhere else. This is just like it's just a toy example for this.
So the point was to show us how to run a program.
On all data files,
Okay.
yeah.
Well,
So-
whatever program that is.
Yeah, it doesn't matter exactly what the program does, it does something.
It does something.
Yeah, that's the idea.
So what does the bash do? It just tells it to run it within the bash?
Yeah, so the thing is, we haven't actually covered that, and we're trying to not cover too much. There are various ways that you can execute a program. We'll see when we start doing Python, we'll see that you can execute a Python program like something like this, where test.py is a Python file. In the same way, if test is a file that contains a shell script, which is what we'll be doing, then you can execute that by doing bash test. So that's basically telling you, test is a file that contains a program. This program should be interpreted by bash or by...
GooseStats is actually a
Yeah.
bash script.
So GooseStats is actually a bash script, which is here. So we can look at what's in there. Which covers some syntax that we haven't actually seen what's doing, but basically it loops through some options, then it sleeps for 2 seconds, and then it does some head and sorting. So the reason that it takes 2 seconds to run is because it's sleeping for 2 seconds. So it's basically just a toy example of a program that's being run with bash. If the thing that you needed to run was a system-wide program installed on your computer, then you wouldn't need the bash there. Then you would just have the name of the program. And per default, you're not allowed, if you do this, then it won't execute it, even though GooseStats is a program in your current folder. That's a security concern in the way that, say that someone created a program called ls and put it into some folder, and that program was actually an alias for removing your entire file system. Then they could trigger you into, when you just ran ls, to remove your file system just by leaving a command, just by replacing ls with something else. So therefore, when bash looks for programs just written like this with the program name, it only searches certain specific directories, so that you can't be fooled into running a different program that does something completely different and unexpected. But doing like this tells the interpreter, yeah, I know what I'm doing, I want to execute this program using in my current folder with bash. Great. Yeah, and I'm going to break it now because we don't have seen that already. And there's a few. So we can look a little bit at the questions relating to this. So we're doing ls that contains 3 different files. And then we're doing a loop over those data files here. And then we're doing ls start.dat or ls data file. So the question is, what's the difference between these two loops?
You'll get a list every time for every file. You'll get a
Yeah, exactly, in the first one. So the first one is most likely not what we want, because in the first one, we'll efficiently replace both of those occurrences of start.dat with the complete list. So we'll first print ls of all 3 files, then we'll run again, print ls of all 3 files, and run ls on all 3 files. So that's, Whereas this one will do ls on the first file, and then ls on the second file, and so on. Exactly. So that makes sense. So if we do something like this for sugar in start.dat, and we've got a number of files again, which are these fructose, glucose, and sucrose, then what's going to happen if we echo and then we cat the file name, so that means showing the contents of the file and piping that into silos.dat. Is that going to print all the file names and then put the contents of the sucrose file into this file? Is it going to print all of them and put all of the contents into that file?
I think you're just going to have the last file, the last file name, there'll be just one name in that file, and it'll just be the last file name.
Yeah, exactly, because the first time the loops runs, it will write that text to that file, but then it will be overwritten all the time. So if we actually wanted to concatenate it, then we would use the double version here. Yeah, which is exactly what this one shows. So I think we've already answered that. If you run through all of these .dat files, and then you use the double concatenation into sugars.dat, then all of them will be concatenated. But obviously we won't get the .txt file in there. Yeah, this is perhaps interesting a little. So I showed before how we could use echo to sort of do a dry, what people call a dry run, where you just print something that tells you what was going to happen if I executed that script, but not actually doing it because it's a destructive command that you don't want to get wrong. If you actually, so you wanted to analyze some file running a program called analyze and piping it into some kind of output, then you could add an echo to see what's going on. But what's the difference between echo a thing and actually echo the thing quoted down here? Anyone want to venture a guess? We can also try executing it. Yeah, so the problem is with the first one, it actually does something that you don't want to, because it's echoing the first two things, and then it's piping that to a file. So the echo only applies to the thing before the character, which is it's not what we want. We actually want to echo all of it because we want to see what the command was going to do. So doing the last one ensures that it won't actually execute anything of what's within the brackets. Otherwise, it would echo that, and then pipe it to the file. I think we'll skip this one with the expression and move on in order to cover some of the last topic before we're done. This is a bit of a sidetrack. So the thing that we're missing now is that we've created this pipeline for running the goostats analysis, but the only way we've stored it is in our bash history. So while the bash history may store everything you've done, then finding a specific command in your bash history that you ran a month ago is probably going to be a horrific experience, and it may not be there anymore because the bash history has a limited length. So we would actually want to put this into a script that we can run again once we've nailed down what we actually want to do. So that's the next topic that we want to cover, how to actually go about putting this into a script. We've already touched about that because we saw how goostats was actually a script that was being run. Yeah, we're going to start with an example on the molecules again, just to get something basic. We talked about how we could use head and tail to find top and bottom of a file, but we also saw that we couldn't actually, there was no way of getting the middle of some kind of some file, because head didn't take a starting position and tail didn't take an end argument, so you couldn't actually with either one of those commands get the middle files. You could combine them to get the middle section of a file, and that's what we're going to see. So let's try writing a script that can do that. So I'm just nano opening middle.sh, which is .sh is the default extension that most people use for shell scripts, but it's just a convention to help you and the computer identify this as being a shell script. Let's say that we wanted the first 15 lines, and then we want to take off the last 5 lines of that. So we could do this something like head 15 octane.dat, and then pipe that to tail and take the last 5 lines.
Is it PDB suffix?
Yes, that is right. So that works. If we execute it the same way we executed the goostats program with bash middle.sh, then we can execute it, and we get 5 lines here that probably are correct. We can look at what's inside the Octane file. So it looks like we're getting lines from down there somewhere. So that looks about right. Yeah. Okay, so this is a fairly simple program, similar to what we've been doing now. It's not particularly flexible. In fact, it's very inflexible, because both the starting number of lines and the end number and the file is actually hard-coded in the program. So if we want to run the same program on a different file, we would have to modify the program. Unfortunately, there's a simple way of getting the arguments into a shell script. So one way, the simple way here, $1 means whatever you put on the command prompt after the name of the program will be put in at that place. So if we replace the file name with $1, then we've actually written a program where we can give it a file name as an argument.
Because I'm putting the text that's in these files in the etherpad so that you can
Great.
always refer back
Yeah.
to that.
So now you can execute it as bash middle.sh, and then the name of the file that you actually want to run it on. And so on. Yeah, and again, as we talked about before, it's probably a good idea to put some quotes around the argument here, because if we had a file name containing a space, it would result in two file names being put to head, which will confuse it. So quoting is a good idea to make this a little bit more foolproof. The next thing we can do, we can make this even more general by also making these start and end points configurable, so we can put in multiple variables. This means that this will be the first argument after the program name, that's the second one over here, and the third one over there. Again, we might as well quote them. It's probably unnecessary, but and the arguments are, of course, still on the same form as they were when given to head and tail, where you need a hyphen, then the number for start and end. Yeah. Great. What do we want to? So a little bit more suppose that we want to sort our files, so we could create a script for doing that, like we've seen before with word count. So the way we would do that normally would be that we sorted all our star.pdb files. Something like this is basically what we've done before. But suppose now that we want to sort all the arguments that we give it after the program rather than sorting a specific extension of files. Then there's a shortcut for doing that as well. So rather than having $1, $2, $3, then the syntax is $at, which will be the complete list of all arguments given to this program. So when I execute it like this, then the first thing that happens is that star.pdb gets completed into the full list of all PDB files, and then that list is given to the sorted program, and it then sorts all the elements in that list.
Can I ask a favor? Could you
Yeah.
Could you keep the file up while you're talking about this, because I'm trying to.
I'm on the Etherpad.
Oh, okay.
Yeah, it would be great if we had a little bit more screen space for doing this, but we'll try making it work with the Etherpad. But yeah, so basically this is close to what we've seen before. The main trick is that this $at will match all possible files, all possible arguments that's given to this program, which comes in handy. The other thing which is confusing is say that we executed the program, but forgot to add what it is that we want to sort. Then it's just stuck like this, not doing anything, because now it's reading, as we've seen before, it's waiting for me to type in what I actually want to do, so it's waiting for standard input of the thing that it needs to sort. So we could add some scripts around protecting that there must be some kind of input, otherwise it should error out with a help message. Same way as when you try to run move without giving it any arguments, then it prints this message. But for now, it's enough to know that if you're in a situation like this, then Control-C will break the program and stop the execution. So again, this *C is shorthand for Control-C. It's always a compromise, right? When you write a script like this for your own need for doing your data analysis, you could spend a lot of time on error handling, making sure that the input is correct and that it prints the right output message and the right errors. But if it's only something that you're going to use for analyzing your own data and which is not going to be widely used by other users, then most likely you don't want to spend too much time on the error handling. On the other hand, you also want to avoid doing something that can enable you to make mistakes that you weren't expecting. Yeah. So again, we talked about how we could use the history to see output. So again, if we say that the last 4 commands we had in our history were actually the commands that we needed to do to use to do something, then we could use head and tail to actually grab those 4 commands and then pipe them into a shell script. So if we do something like this, history, that will print the history. Then we pipe that to tail, grab the last 4 lines, and those 4 lines we just put in a myscript.sh file. Then the myscript.sh will contain those 4 lines, and say we didn't want, then we can quickly write a shell script if those were actually the lines by just editing this thing. So that's a quite typical pattern for how you're working with these things, that you use the interactive shell to figure out exactly what you want to do, and then once you've done that, then you can use history and various other commands, either tail or head or copy pasting, to move those lines into a shell script and write a finished shell script. So again, back to what we're actually working on, Nell's analysis script. We want to create a program, we could call it run goostats, that actually runs goostats on our data files. We figured out that the thing we wanted to run was something like for data file in the list of data files. We can again use this syntax, which is wrong, syntax like this, to ensure that we're actually using a command line argument to our shell script to get the names in there. Now we're just going to write it again, but of course we could use the history to find these commands. It happens that goostat takes some arguments that that we need to use. So we'll enter those in as well. So now we've written a bash script that takes an input list of argument, then it runs over a for loop, prints the name of the data file, runs goostats with some options. But we're not overly concerned with what they're doing, but we've been told to run it with those options on a data file, outputs it in another in a statistics data file, and then we're done. It's probably relevant to document what this kind of program is doing. So in Bash, all lines that start with a hash character are command lines.
I guess I'll just try to get a copy of that.
So something along the lines of what this is actually supposed to be doing is probably handy. So we can now do bash, run the goostats program, and again we want to run it on all the AB files.
I'm just kind of got behind because I was trying to get one script working.
So just to make sure that we've gotten rid of all stats files before we run it, we can remove those. And then we run goostats on all -AB files. So now we've gotten as far as creating a small script that can actually do our statistics calculations on all the data files automatically. And we can rerun the script in a month or 2 months if we decide that we want to rerun it, and it's easy to modify and tweak the script to do something different. Yeah, so it's a matter of exactly what you want to do, whether you want to run the script like this, where you have to supply the file names as an end, or you actually want to hard code the file names in there. So it could be that you knew that you were only going to ever be interested in running this on the AB files. Then you could just write it like this. That means that you don't have to remember to exclude the non-AB files. It also means that the program is less flexible. So that's a matter of taste and a matter of exactly what you need to use the program for, whether one thing or the other makes the most sense. It could also be that it would make sense to have another shell script which called this shell script with the star.ab, so that you had one program that actually looped over it, and then you had one program that contained the list of files that you wanted to run on, so that you separated it into two. Yeah. Any questions about this? We should probably see if everyone can get this kind of thing running, because that's sort of the main goal of the lesson to be able to write this shell script and have it running. If you've got that, then put up a green sticky note, and then we're probably coming up towards the end of the session. It looks like we won't have time to go into the last section, which is about using two commands called grep and find to search files and directories, which is unfortunate because it's very handy and very useful, but yeah, you can feel free to read it afterwards at some different time. Any questions or? So one thing that keeps coming up is that it runs it across the stats files, and it creates the stats of the stats. So it's probably a good idea to ensure that the file starts with what the file is expected to start with. So all the files start with NE, whereas the stats files don't. So if we change the pattern that we're trying to match from just being star ab.txt to neen star ab.txt, then it will only match the original files.
Some of you have also learned that it's important for these commands to all be on the same line, because a new line, this bash thinks it's a new command if it goes to the new line, so you can't spread things out across multiple lines. There is a way to do that with a special character that means like this command continues on the next line, but we haven't seen that yet.
Yeah.
But do go to the shell lesson, the finding things lesson in the shell things, and read that when you get a chance, because find and grep are really handy. But it is lunchtime. We will see you back here at 1 o'clock for some Python with Katie and Thomas.